Hello guys, welcome back to the Basics of Mechanics lecture series. I am Barney Deepak and today we are going to learn about friction and friction force. In this video, I'm going to give you a few real world examples to help you understand about friction in a better way. Also, we will come up with an expression to calculate the friction force of a given system. So let's begin. Okay, friction is essentially a contact phenomena which happens between bodies when either one or both of them are in motion. Also, it is fair to say that whenever there is a contact between two moving bodies, there will be a friction force developed. The friction force has a lot of applications in the real world. For example, imagine you are riding a bike on a dry and hard surface. When you pedal, you move forward. Now, this implies that the wheels of the bike are gripping on the dry surface and rolling over it instead of slipping and sliding. This is due to the presence of a significant friction force between the tire and the road surface. Now, if you're riding the bike on a snowy and a wet surface, your tire might experience a slip and it might slide over the wet surface instead of gripping it and rolling forward. This is a clear example of a case where there is not enough friction between the tire and the road. So from this, you might quite understand that how important friction is to our day-to-day life. Let us consider a rather simple example of two blocks which are placed one over the other like this. Now assume that both the blocks are stationary. We can simply denote the forces in the systems like this. Self-weight of the block A will be acting downwards and the reaction force from B will act upwards to keep the system in equilibrium. Let us now try to apply a force F on the block A and move it over B. When we try to do this, due to the contact between A and B, there will be a friction force Fr which will be developed parallel to the contact surface, and most importantly, this friction force will be acting in the direction opposite to the movement of the block A. Alright, now let's consider that this system is in equilibrium and apply the conditions for equilibrium to get some relation between the forces acting on the system. First up, we know that for an equilibrium system, the algebraic sum of all the horizontal and vertical forces are 0. So summation of Fv, which implies the sum of all vertical forces, will be equated to 0. Here the vertical forces are the self-weight W and the reaction force R, which will be equal to each other. Similarly, applying the conditions for the sum of horizontal forces, summation of Fh is equal to 0. We have the applied force F is equal to the friction force developed Fr. Now wait, does this make any sense? Though we have considered the equilibrium condition, is it correct that the friction force which is developed will be equal to the force that is being applied? What this equation says is the friction force Fr at any instance will be the same as the applied force, which means at any given point the applied force will be offset by the friction force. If this is true, you can't move anything over a surface. But in reality, it is evident that you can push objects and move them, right? So an important consideration that has to be kept in mind is that the friction force which is developed on the contact surface has a limit. It cannot go as high as the applied force. To represent this in a better way, let's draw a graph between the applied force and the friction force, with applied force on x-axis and friction force on y-axis. Assuming that I want to push a heavy block and move it to the other side of my room, I will constantly increase my force on the block to make it move. For a while, as long as my applied force reaches the maximum friction force, it can't move the block, because the friction force developed will resist the motion of the body. Once the applied force is over and above the maximum limit of the friction force, the block will start to move. In this case, the friction force will stay at its maximum value. For us, it will be nice to know the maximum friction force which will be developed. To have this, we need to observe the ratio between the friction force and the reaction force. This ratio will be a constant for any system. This constant is called as coefficient of friction and its value depend on the type of material of the surface. When you rearrange this relation to get the friction force, you will get Fr, the friction force, is equal to mu times R. Okay, now let's apply all these concepts to this problem. You have a block A with a weight of 120 Newton resting on block B. If the coefficient of friction between the surface is 0.6, what will be the minimum force required to move the block A? Now the very first step to solve this kind of problem is to identify all the forces acting on this body. Now we know the self weight as 120 Newton. The reaction force for this self weight will be equal to 120 Newtons. Also, in the previous section, we learned about the friction force that is being developed when two bodies are in contact. The calculation of friction force is as follows. Fr is equal to mu times r. Now this is the maximum friction force that will be developed in this system. So we have 0.6 as the friction coefficient and r the reaction force as 120 newtons. So solving for the friction force Fr, we will have 72 newtons. So now we got the maximum friction force of 72 newtons. What does this mean? Well, this means that if the applied force is less than 72 newton, then this applied force will be very much offsetted by the friction force that is developed between the contacts. So the body A would require a minimum of 72 newton force to make it move over the body B. Before we move forward with the more complex example, let me distinguish the behavior of the friction force in theory and in practice. We saw that the friction force developed between the surfaces will reach maximum and stay maximum after a particular applied force. However, this is applicable only in theory. In the real practical case, the friction force will reach maximum and after the body is in motion, the friction force will drop down from its maximum value. Okay, now let's move on to our second example. Here we consider a block which is placed in an inclined surface. The angle of inclination is 30 degrees and the coefficient of friction between the surface and the block is 0.2. The block has a weight of 100 newtons. What will be the minimum force required to push the block up the slope? Now this is a bit tricky problem. You can see that the self weight of this block, half 100 newton, is acting diagonally in downward direction. Now what we have to keep in mind is that the reaction force R will be acting always perpendicular to the contact surface. So in this case we cannot apply the conditions of equilibrium and directly consider the reaction force as the self weight of the block. So what we need to do is we need to resolve this inclined force of self weight of 100 newton into horizontal and vertical component so that it stays analogous to the applied force or to the reaction force. So for which we need either this angle or this angle. So to calculate that, let's redraw this diagram. First you have the inclined slope of 30 degrees. Then you have the block here. So if the self weight acting downwards, if I extend this line, you have a right angle triangle like this. This one. This forms 90 degrees and the remaining angle, this will be 60 degrees. And let this be the line of action of the applied force P. And this be the line of action of the reaction force. This will be 60 degrees. And again, when you zoom in a bit, this again will form a right angle triangle. This will be 60, then this will be 30 degrees. And this side will be 60 degrees. So now that we have the angle 60 and 30 degrees, we can take either one of these and resolve this self-weight force into the horizontal and vertical components. So for the convenience, we have the inclination angle as 30 degrees. So let us take 30 degree as the angle of inclination of this inclined self-weight and resolve that into its horizontal and vertical forces. Now I have redrawn the system. When I resolve this 100 Newton of self-weight into the horizontal component, I have 100 sine of 30 degrees. So this will be the horizontal component, and the vertical component will be 100 cos of 30 degrees, which will act downwards. So alright, now we have the horizontal and vertical components of the inclined self-weight. What we got to do now is we can now apply the conditions of equilibrium and try to calculate the force that we required. So according to the conditions of equilibrium, we have summation of all the forces in the horizontal direction as 0 and the summation of all the forces in the vertical direction as 0. So the vertical forces acting on this system is 100 cos of 30 degrees minus the reaction force is equal to 0. So from this we can get the reaction force as 100 times cos of 30 degrees, which is 86.60 Now if I apply the first conditions of equilibrium, that is the summation of all the horizontal forces is 0, I get F is my horizontal force, then the horizontal component of the self weight as my horizontal force, and then if I'm applying the force in this direction, I will have a friction force that is developed in the opposite direction. So Fr, this will be the opposite direction. So that's it. So that these three are the horizontal forces. Alright, so if I apply summation of FH is equal to 0 as P minus 100 sine of 30 minus Fr. So this will be equal to 0. So Fr by definition will be mu times the reaction force. So P minus 100 times sine of 30 minus mu, in this case is 0.2 times R equal to 0. So when we substitute all the values and calculate the force that is required P, we will get 67.32 newtons. So yeah, so 67.32 Newton is the minimum amount of force that is required to push this block up the hill of 30 degrees of inclination. So that is how you need to calculate the force required by considering the friction force in order to move a body. I know this will be a little confusing step because we are considering an inclined system and we have to consider this angle of inclination into our problem solving steps. So if the forces acting on the block placed on an inclined surface looks complicated to you, here is another detailed view of the system for your better understanding. Okay, so that's it guys. I hope this video was useful for you in understanding about the concepts of friction. If the video was helpful, please give us a thumbs up and subscribe to the channel. Also share the content with your friends who might find it useful. Thank you once again for watching the video and I will talk to you guys later. Bye bye.